Welcome everyone to the 18th lecture in the lecture series on circuit and system. I am Nikhil Kumar Nigam from EEE Department, Delhi Technical Campus. In the last few lectures, we have been discussing the time response analysis of circuits, and over there we analyze that the analysis of circuits using the in the time domain is quite difficult because of the presence of differential and integral equations. The solution of integral equations or differential equations is quite difficult, so we come up with another method, which is employing the use of Laplace transform for the analysis of circuits. I would say that Laplace transform is a boon to engineers, because all the physical activities or for all the physical systems involve the differential and integral equations, and to do their analysis we needed a medium which could simplify the solutions into the equations that are very easy to solve, like the linear equations. So this is what exactly the Laplace transform do. It transforms the integral differential equations into the linear equations, which are very easy to solve and analyze. So let us start today's lecture. So in today's lecture we will be discussing about the circuit analysis using Laplace transformation. You may have read about the Laplace transform in the mathematics subject, so I'll not be going into the depth. I'll be using this Laplace transformation to do the circuit analysis only. I'll be giving you the upper touch of the Laplace transform only. So let us start. The first question arises, why Laplace transform? Because we have discussed that in time domain analysis, we have integral differential equations, equations that define the system, and the solution of these integral differential equations involve the calculation of complementary function as well as the particular integral, and also with the use of initial conditions. That is, we first calculate a general function or general solution, then we using the initial condition we finally get the result. So in the time domain analysis we have integral differential equations, and their solution can be found using the complementary function, particular integral, and initial conditions, and this poses very difficult solutions or difficult mathematical problems. These are very difficult mathematical problems. So why the time domain analysis approach is not used or is not famous? This time domain approach is also termed as the classical approach of analysis. But what if we could convert these integral differential equations into linear equations? Then manipulate them to get the answer. So this is what exactly the Laplace transform does. It converts the integral differential equations into the linear equations which are very easy to solve, and then we manipulate these equations to get back the result. So this is Laplace transformation. Laplace transform. So how does this integral differential equation gets converted into linear equation using this Laplace transform? What it does that in the time domain analysis, the equations are in the time domain, that equations are the functions of time, but in we convert them into the another linear equations in the variable s. That is, we remove this variable t and then we convert this system into another system which has a variable s. Now these equations will be linear equations. They will not involve any kind of differential part or integral part. That is why the introduction of Laplace was a boon. Laplace was a boon to engineers. So we'll discuss more on it. So while finding out the solution using the classical approach, we will have integral differential equations, which are solved to get the solution. This is the classical approach, but in the Laplace domain approach, first the integral differential equations which are defined in time domain are converted into S domain by Laplace transformation. Then after the Laplace transformation, we had linear algebraic equations, and we have already discussed in the 8th class, 9th class, 10th class then how to solve these linear equations. But these linear equations are in S domain, are defined in S domain. So these linear equations are defined in S domain, that is, instead of time domain now we have S domain. And while defining or while converting into the S domain, it already takes care of initial conditions. That is, we do not need to separately look for the initial condition to find the complete answer or complete solution. In this, the initial conditions are already considered while converting into the differential equations. So after the conversion of the integral differential equations into linear algebraic equations, we manipulate them using partial fraction method, and then whatever we had in the in the output, we convert that into inverse Laplace form. Then this inverse Laplace will provide us the solution in the time domain. So the advantages with the linear Laplace transformation is that it converts integral differential equation into linear algebraic equation. Also, it takes care of initial conditions automatically, whereas in integral differential equation solutions we need to perform another step to find out the complete solution using the initial conditions. So these are the advantages. Let us now define how a Laplace transform converts the time domain equation into an S domain equation. Suppose we have a function f of t which is needed to be converted into S domain by Laplace transformation, then we get another function in S domain. And how this transformation occurs? I can define the Laplace transform of ft as f of s, capital F of s, to be equal to the integration of f of t from 0 to infinity f of t times e raised to power minus st dt. Now this integration converts the time domain function into an S domain function, where this S variable is termed as Laplace operator. And while doing the analysis of circuit, we consider this S to be a complex variable, complex frequency variable, where this S is equal to sigma plus j omega. As it is a complex quantity, so it will have real part as well as the imaginary part. So this real part is sigma and the imaginary part is omega. So this is S operator in the Laplace transformation. And if we have f of s, we need to convert it back into the time domain to get the ultimate answer. So in time domain, this f of t can be written as 1 by 2 pi j integration from sigma minus j infinity to sigma plus j infinity f of s into e raised to power st ds. So this is the inverse Laplace transform. This is let us discuss some properties of Laplace transform. The first property is, before discussing the property, let me state that if we have a function f of t in time domain, and after Laplace this function is represented as capital F of s. Mark here that while representing any function in Laplace transformation, we will generally use the capital letters. It is the convention. So if f of t after Laplace transformation becomes f of s, then the first property is the scaling property. That is, if I have k f of t, that is the function has been scaled by a constant, then its Laplace transform will be k times f of s. That is, the scaling factor will not be altered while transforming from time domain to S domain. The second property is the property of additivity. Now this property states that suppose I have a function f1 of t and which is getting added up with the another function f2 of t, then its Laplace transform will be, it says the Laplace transform of the two functions which are added can be distributed, and it will be equal to f1 of s plus f2 of s. So the Laplace transform of f1 of s was f1 of t was f1 of s, and the Laplace transform of f2 of t was f2 of s. Then the Laplace transform of their addition will be equal to the Laplace transform of their individual functions and adding them up in the resultant. This is the additivity property. Let us discuss the third property. The third property is time differentiation property. Time differentiation property. And this property says if the Laplace transform of f of t is f of s, then the Laplace transform of its derivative will be given as sfs minus f of 0 negative. That is the Laplace transformation of a differentiation of a function is equal to s times the fs. Fs is this, that is the Laplace transform of f of t. So if we have the Laplace transform of f of t, and to find the Laplace transform of its derivative, then what do I need to do? I need to multiply this fs with s only, and then I need to subtract the initial condition. See here, the initial condition has already been taken care in the example here. And similarly, if I had the nth derivative, say I had this is another derivative, nth derivative of the function f of t with respect to time t, then its Laplace is s raised to power n f of s minus s raised to power n minus 1 f of 0 negative minus s raised to power n minus 2 f dash of 0 negative minus s raised to power n minus 3 f double dash of 0 negative, where f dash f double dash are the time derivative of the function f of t, and their values have been evaluated at t equal to 0. So this is the derivative of the function at for the nth derivative. Okay, the next property is the time integration property. Let me first write f of t is converted into f of s after Laplace transformation. Then the fourth property is the time integration property. That is, now I have the time integration of the function f of t dt, and I need to find out its Laplace transform. Then its Laplace transform will be given by f of s by s. That is, we just need to divide the function Laplace with s to get its derivative, or to get its Laplace transform. Okay, if we have more integrations, say if we have double integration, or like this, if we have n integrations here, and then we are taking the Laplace transform of the function, then it will come out to be f of s divided by s raised to power n, and we have assumed the function f of t to be defined for, f of t is defined for t greater than 0. This is only valid if the function t is defined for t greater than 0. The next property is frequency differentiation property. In this, suppose we have this function t f of t, that is, the given function is multiplied with this t, and then we are required to find its Laplace transform. Then its Laplace transform will be the frequency derivative of the Laplace transform of f of t, which is f of s here. So if a function is multiplied with time in the time domain, then its Laplace transform will be the differentiation differentiation with respect to s of the Laplace transform of the function. Next we have frequency integration property. Just like the differentiation property, we have frequency integration property. If we have f of t and it is divided by time t, then its Laplace transform will be the integration of f of s from 0 to infinity. Well, these two properties are very rarely used in electrical science, so they do not need to be remembered, but the differentiation, time differentiation and time integration properties are very frequently used, so remember them, especially this one and the last one. Let us move ahead. Now we have time shifting property, very important property, time shifting property. That is, if we had a function f of t whose Laplace transform is f of s, then the Laplace transform of time shifted function, that is t minus a, that is this has been time delayed, then this will be the Laplace transform of this function will be e raised to power minus as into f of s. That is, the time delay in it will multiply the Laplace transform of this function with e raised to power minus as. Next we have frequency shifting property. That is, if I multiply the function with e raised to power minus t with the function, then its Laplace transform will be frequency shifted. It will be s plus a. And if I multiply e raised to power at with f of t, then its Laplace transform will be f of s minus a. That is, whatever is the component here, its negative will be added here. That is, we had a here, so its negative is added here. If we had minus a here, so its negative is added here. Students generally get confused between the time shifting and frequency shifting formulas or the properties. Remember, here in time shifting, whatever component we had here, it will be present into the s domain, but in frequency shifting, whatever we had here, it will be reversed, or it will be the negative of it will be present into the frequency domain. Okay, next we had initial value theorem. Initial value theorem. Now this states that the initial value of the function, that is limit t tends to 0 positive f of t. This is the initial value or the transient value of the function. This will be equal to limit s tends to infinity s of fs. So this is giving the initial value of the function in time domain, so why it is termed as the initial value theorem. Just like this, we have final value theorem. Final value theorem, that is limit t tends to infinity f of t that is the final value of the function at t equal to infinity will be equal to limit s tends to 0 s of fs. Now if I solve it, I will get the final value. By final value I mean the steady state value. Steady state value, that is, by using this I can calculate the steady state value, and by using this I can calculate the transient value. There is a condition with this final value theorem, that this final value theorem is not applicable for periodic function. So it is not applicable for periodic function. So if f of t is periodic, let us assume that f of t is sin omega t, then this value is not applicable. This is not applicable. Let us now see the Laplace transform of some common signals that are used in electrical science. The first one would be a step signal, unit step signal, generally represented with u of t, and if I had to take the Laplace transform of this, then it will be 1 by s. The Laplace transform of ut is 1 by s. The second is the Laplace transform of a ramp function, unit ramp function, rt. Then this will be, its Laplace transform is 1 by s square. Laplace transform of say impulse signal delta t, then its Laplace transform would be 1. Similarly, the Laplace transform of an exponential signal, e raised to power minus at, then this will be 1 by s plus a, and if it had been e raised to power at, then its Laplace transform would be 1 by e raised to power s minus a. Next is sinusoidal signal. Sinusoidal signal or sine signal, say I have sine omega t, and its Laplace transform is given by omega divided by s square plus omega square. And similarly, the cosinusoidal signal, cos omega t, then it will be s divided by s square plus omega square. Students also get confused between these two formulas because these two formulas appear to be very similar. So how do I remember? I will tell you. See here, we have sine omega t, and it is coming out to be omega by s square plus omega square. We have cos omega t, which is coming out to be s divided by s square plus omega square. So the difference between the two formula is the presence of omega or the presence of s. So I remember it. If any trigonometric function ends with s, then it will have s in the numerator. If it does not have ends with s, it will not have s in the numerator. So this is the way I remember. You can choose your own way. Let us move ahead. Say I have sine hyperbolic function, sine hyperbolic omega t, then its Laplace transform would be omega divided by s square minus omega square. And similarly, if I have cos hyperbolic signal, cos hyperbolic omega t, then I will have s divided by s square minus omega square. So let us remember these properties and these formulas, or the Laplace transform of various signals, and let us now perform some numericals based on it. So the first numerical is, we have to find the Laplace transform of k times u of t minus a. Let us find out the Laplace transform of k times u of t minus a. It is a unit step function, delayed unit step function, which is scaled to the factor k. We already know the the Laplace transform of ut is equal to 1 by s, and we can use the time shifting property. We know that f of t minus a is equal to e raised to power minus as times f of s. So here f of t is ut, so ut minus a, so the Laplace of ut minus a would be, so the Laplace of ut minus a would be e raised to power minus as into f of s, but f of t here is ut, so the Laplace transform of ut is 1 by s, so I will multiply it with 1 by s. So the answer is e raised to power minus as by s. But this function is scaled, and we already know by the scaling property that the scaling is not transformed, it is kept the same. So the final answer of the Laplace transform of k u of t minus a, the Laplace transform of Laplace transform of k u of t minus a will be k times e raised to power minus as divided by s. Let us find the Laplace transform of delta dash t, that is the derivative of the impulse function. We already know that delta t has a Laplace transform of 1, so its derivative would be having a Laplace transform of delta dash t would be having the Laplace transform which is equal to s times f of s, or f of s here is 1, so this will be s only. So the Laplace transform of delta dash t is s. Let us perform the next numerical, e raised to power minus at into sine omega t. Now we have to calculate its Laplace transform. If I consider this to be ft, then ft is multiplied with e raised to power minus at, and it will be similar to the frequency shifting. So let us find out the Laplace transform of omega t first, f of t first. So the Laplace transform of sine omega t we already know is equal to omega divided by s square plus omega square. As it is not ending with s, so I will put omega in the numerator, omega divided by s square plus omega square. Now using the frequency shifting property, e raised to power minus at into sine of omega t should be equal to f of s minus a, s plus a, its inverse should be added here. So the Laplace transform of e raised to minus at sine omega t should be, I will replace s with s plus a. So in this function I will replace s with s plus a, so I will get the solution as omega divided by s plus a. square plus omega square. So this is the solution. Let us perform another numerical. Say we have e raised to power 2t, e raised to power 2t cos of t, and we have to find its Laplace transform. So the Laplace transform of cos t will be s divided by s square plus omega square, and omega over here is 1, so it will be 1 square means 1. So cos omega t, so cos t will have a Laplace transform of s divided by s square plus 1. So when multiplied with e raised to power 2t, we will use the frequency shifting property. Using frequency shifting property, we will get the Laplace transform of e raised to power 2t into cos t to be, now we will replace s with s minus 2, that is we will add the negative of this component into s. So now we will replace s with s minus 2 divided by s minus 2 square plus 1. So this is the Laplace transform of this. Similarly, let us calculate the Laplace transform of e raised to power minus at into t into ut. So we already know that the Laplace transform of ut is 1 by s, and when it is multiplied with t, we will use the frequency differentiation property, that is t into ut will be equal to differentiation of 1 by s, and this will come out to be 1 by s square. The property is that when we multiply any function with t, we get the negative differentiation of f of s. So the negative differentiation of this will be minus 1 by s square, and we already have a minus, so this will give 1 by s square. So the Laplace transform of t ut is 1 by s square. Now we will use the frequency shifting property, as the function, this function is being multiplied with e raised to power minus at. So using the frequency shifting property, I will shift s with s plus a, that is I will add the negative part of it. The negative of minus a is plus a, so I will add negative part of this in the s, and now I will replace s with s plus a in the above function. So the Laplace transform of e raised to power minus at into t ut will be equal to 1 by s plus a whole square. In the next numerical, say we are required to find out the Laplace transform of g12 t, which is a gate signal, and we have to find out the Laplace transform of this. This gate signal can also be represented as u of t minus 1 minus u of t minus 2. So the Laplace transform of this would be, let us first find out the Laplace transform of this. We already know that Laplace transform of ut is 1 by s, so the Laplace transform of ut minus 1 would be we will use the time shifting property. We will multiply this with e raised to power minus as, or a is 1 here, so I will multiply it with minus e raised to power minus s and 1 by s. Similarly, the Laplace transform of u of t minus 2 would be e raised to power minus as, and a over here is 2, so I will multiply it with e raised to power minus 2s into 1 by s. So now putting these two into this, I will get e raised to power minus s into 1 by s minus e raised to power minus 2s into 1 by s. So this is the Laplace transform of this signal. So in this lecture we discussed the introduction to the Laplace transform and how we can utilize the Laplace transform to solve integral differential equations. In the next lecture we will discuss some topics of partial differentiation, and then we will use this Laplace partial fraction, and then we will use this Laplace transform method to analyze the electrical circuits. Till then, bye bye, take care, and keep reading, keep studying.